You may have noticed a few times throughout the lecture so far, I've indicated that this y sub p that we pick is our quote-unquote initial choice of y sub p. And I mentioned earlier that when it comes to selecting this y sub p, there's a complication that can arise that will force us to throw out our initial choice of y sub p. We have to modify it to accommodate this complication. I'd like to kind of demonstrate that complication through example 4, and then we'll talk about the procedure for addressing this issue. Here I've gone ahead and solved the homogeneous version. So I know that my y sub h is c sub 1 e to the negative 2t plus c sub 2 e to the 3t. And then based on the previous example, since this right-hand side is an exponential e to the 3t, then I will try y sub p to be some constant times e to the 3t. I calculate the appropriate derivatives. I plug those derivatives into my original differential equation. And now when I go to try to simplify and solve for the coefficient a, something bad happens. Here I factored out the e to the 3t on the left, and when I simplify this coefficient, I get 0 times e to the 3t equals 4 e to the 3t. That is to say, 0 equals 4 e to the 3t, which is of course a contradiction because e to the 3t can never equal 0. So applying my previous method seems to have failed me in this case. So what's the issue here? What caused this problem? As I try to describe below, the problem is that this component of my homogeneous solution is matched by the type of function that I'm trying to choose for my y sub p. The way that I'll usually say this is that there's repetition between some term in my y sub h and some term in my y sub p. Clarifying that a little bit in the next paragraph, this actually has to do with this notion of linear independence. And one way to think of that is that if I was to form a general solution built out of this y sub h plus the y sub p that I had selected, then this e to the 3t term would effectively get absorbed into the e to the 3t term that already exists in my y sub h. And so in that sense, my general solution y would be deficient. In the next paragraph, I remind us that this is kind of similar to the issue we ran into back in section 3.4. In section 3.4, our characteristic polynomial had one real repeated root, say r. And back then, we were tempted to just use e to the rt and e to the rt as two separate functions to build our general solution out of, but we couldn't do that because those two functions were not linearly independent. Our solution back then was to multiply this second term by some function. And we used the simplest function we could think of, namely the function t. So we multiplied this second component by t. It turns out this is exactly the same approach we will use here. Specifically, we will multiply by t or increasing powers of t as necessary. So maybe t isn't sufficient, so we need to multiply by t squared. If that's not sufficient, we need to multiply by t cubed. So we need to multiply by increasing powers of t until the repetition between a component in y sub h and a component in y sub p is eliminated. With this strategy in mind, let's try example 4 again. So this time, instead of just selecting y sub p to be some coefficient a times e to the 3t, I've introduced this t here as a multiple so that the repetition between this e to the 3t term and this one is eliminated. Now that I've modified my y sub p appropriately, the rest of the problem should play out as it would have previously. So I've worked through pretty much all of the steps. For here, I calculated my appropriate derivatives. Double check that I did these correct. I have to apply the product rule and then I have to kind of collect like terms, but those should be right. I've taken those derivatives, plugged them into my original non-homogeneous full differential equation in the appropriate way. And then the two types of terms that I have in this equation are t e to the 3t terms. I've undersquiggled those in this kind of greenish color. And then I also have just a constant times e to the 3t. Those I've underlined in pink. When I set like coefficients equal, it'll be the coefficients on those two types of terms that determine the resulting equations. If I look at the t e to the 3t terms, on the left, I have 9a minus 3a minus 6a. So I actually have 0. On the right-hand side, I also have 0 because there is no t e to the 3t term on the right-hand side. Playing the same game with these e to the 3t terms, I have 6a minus a. So that yields 5a equal to 4 because, again, I'm just grabbing the coefficient from the e to the 3t terms. So that tells me that a is 4/5. I can plug that back into my y sub p, so I have a full y sub p. Then I'll simply add my y sub p and my y sub h, and that'll give me my general solution. So here's my general solution, and in a sense, I have three linearly independent functions that this general solution is built out of. So introducing that t forced this e to the 3t in this last term to in fact be distinct or nice enough so that I can actually build my general solution out of those. We will kind of repeat the process that we did in example 3, where we're not going to go through and do the full calculations to actually solve the general solution. We just want to focus on what we would pick for y sub p. And I imagine that in this example, we're going to need to account for potential repetition between y sub h and the y sub p that we would want to pick. So let's take a look. In order to identify potential repetition, I need to identify y sub h as a first step. So let me do that first. So I believe this will be my y sub h. And if I make this initial choice for y sub p based on the structure of my g of t, I do notice that there is repetition between this e to the 3 term in my y sub p and an e to the 3 term that I have in my y sub h. So this will not work as my y sub p. So I introduce a t multiple on this term that's repeated, and then notice that this e to the negative 5t is not repeating anything in my y sub h, so I can actually leave that term alone. So the y sub p that I would move forward with is this one here. In the next example, I have the same homogeneous version, so I'll have the same y sub h, so I'll just keep that there for reference. And then based on the general guidelines for choosing my y sub p, since I have a linear function times e to the negative t, my y sub p would have the form a general linear function times e to the negative t. Notice here that I've left off this coefficient because if I was to distribute through, every term would have a unique coefficient. So having an additional coefficient there would be redundant. But then also notice that this exponential term is going to repeat with the e to the negative t that's already in my y sub h. So I have to multiply by t in such a way that it eliminates that repetition. If I just multiply this coefficient b by t, for example, then I once again run into this issue of linear independence and dependence. That at and bt would get absorbed into a single term, and so I wouldn't have enough terms. So instead, I have to multiply this entire expression by a t. Here, let me actually distribute that out. And when I've gotten rid of all the parentheses, you can see more clearly that now there is no repetition between any of the terms in my y sub p and any of the terms in my y sub h. On part C, notice that I have a new left-hand side, so let me identify the y sub h first. And then based on the fact that my right-hand side is sine of t, my initial choice for y sub p would be y sub p equals a cos of t plus b sine of t. And now comparing my y sub p with my y sub h, there is no repetition. And so I don't have to adjust this y sub p at all. And in this particular case, this initial choice will in fact work. In part D, I have the same left-hand side, so I'm referencing this same y sub h. Since my right-hand side is 9e to the t, my initial choice for y sub p would be ae to the t, but there's clearly repetition between this e to the t term and the same term in my y sub h. So that choice of y sub p won't work. My technique for addressing that repetition is to multiply this y sub p by t. So when I do that, I get this new choice for y sub p. But notice there's still repetition between this term in y sub p and one of the terms in my y sub h. Therefore, I need to multiply by a t again, in a sense. I have to multiply by a higher power of t. So this choice of y sub p won't work. And now I have a t squared e to the t. This is what is meant by multiplying by increasing powers of t. First I multiplied by t, now I'm multiplying by t squared. Finally, I have a linearly independent function from the two components in my y sub h. So this choice of y sub p will work. Let's take a look at part E. First, note the new left-hand side. So this will be the new y sub h that I will reference. And then my initial choice for y sub p will look something like this. I've got a sine of t term in my g of t. So that requires me to include a cosine of t and a sine of t terms in my y sub p. And then I also have a cosine of 2t term. So that requires me to include cos of 2t and sine of 2t. But I notice repetition between these cos of 2t, sine of 2t terms, and the same terms in my y sub h. These terms, cos of t, sine of t, are not repeating, so those can be left alone, and I'll just multiply these terms here by a t. So I'll have a y sub p that looks like this. Let's take a look at just a couple more examples here in part F. I have a new left-hand side. So I have noted the corresponding y sub h. I make this initial choice for y sub p, and now it appears that I have repetition because I have a cosine t term and a cosine t term, similarly with these sine of t terms. But before I modify this y sub p, I need to recall that these cos and sine terms over here are actually multiplied by e to the negative t. So they are not just cosine of t, for example. This term here is in fact e to the negative t cos of t. So there is no repetition, so this initial choice of y sub p will work. In part G, I can already tell that it's not going to be the same because I do have an e to the negative t sine of t. My initial choice of y sub p would be a function like this. I've got an exponential multiplied by a sine term. So my y sub p has to be a general exponential multiplied by cosine plus sine term. This is a perfect match for my y sub h, and so this will not be feasible for my y sub p. So I have to multiply this entire thing by t to get a y sub p of this form here. Let's finish things off by doing one last example, a full example where we find the general solution and then also incorporate initial conditions. Let's take a look. Example 6, we're asked to solve y double prime minus y prime minus 2y equals hyperbolic cosine of 2t. This is sometimes pronounced cosh of 2t. And this, we saw hyperbolic sine in a previous example, and the definition for hyperbolic cosine is very similar. Let me remind you what that is. It is nearly the same fraction as hyperbolic sine, except I've changed the sign, S-I-G-N, in the middle. So notice I have hyperbolic cosine of 2t, so I'll be plugging in 2t. So my right-hand side will become a sum of a couple of exponentials. So after making that substitution, this is what my original ODE looks like. As always, I start by first solving the homogeneous version. So I found my y sub h. Now I make an initial choice for y sub p based on the structure of this right-hand side. This right-hand side is two exponentials, so my y sub p will be two corresponding exponential terms. I note that I do have repetition between this e to the 2t term in my y sub p and the same term in my y sub h. So that'll force me to modify my y sub p. I've introduced a t on that term to eliminate that repetition. The second term here, which is not repeating anything in my y sub h, just gets left alone. And now I move forward with the usual steps. I'll find the appropriate derivatives and plug them in to my original ODE. Here are my derivatives. Now let me scroll down and plug those into my differential equation. Now, having plugged in those derivatives, notice I have three different types of terms. I have t e to the 2t. I have just a constant e to the 2t, and then a constant e to the negative 2t. So I should have three equations. Setting like coefficients equal gives me this system of equations here, which is pretty easily solved. I had to get these a and b values pretty directly. And then that allows me to state my general solution, which I have in this box here. But recall that we were given initial conditions in the statement of the problem. So this is my final answer. I need to move forward and incorporate those initial conditions. Here are those initial conditions as a reminder. In this first equation, I've gone ahead and plugged in t equals 0 into my general solution, and then I've set that expression equal to 0. In order to incorporate this second initial condition, I need the derivative of my general solution. So I've evaluated that here, and now I plug t equals 0 into this expression. That's what I get here, and then I set that equal to 0 as well. So I'll have these two equations here, and I need to use those to solve for C1 and C2. Let me start by just cleaning them up a little bit. So I'm actually dealing with this system of equations here. It appears that I can add these two and that'll eliminate C1. Again, at this point you can use whatever algebraic techniques you're accustomed to solve for C1 and C2. So, solving that system for C1 and C2, I believe I get these values here. It's kind of a lot of fractions and stuff going on, but I believe these are my values. So I can plug those in to my general solution, and I'll have my final actual solution to this differential equation. And I get this final solution in the box here. A lot of work on that problem, kind of some tedious algebra and working through all the calculations, but it helps demonstrate this entire process from start to finish. So in this section, we've looked at one method, the method called Undetermined Coefficients, that enables us to solve a non-homogeneous, linear, constant coefficient ordinary differential equation.